So this is the last video for the Prax, the specified Prax. This one is for waves 3.5. It's all on wave speed, and me and Mr. Mulroy are going to carry out the method, the experiment. So here we go. So we're here with the last practical for year 10, investigation of the speed of water waves. And we've got a nice little tray, like it's demonstrated. We've got a couple of rulers and a stop clock in the shape of a foam. And we've got a nice table of results. First thing I want to just point out is that we're not going to do an average here, a mean, I should say, like it suggests. And especially when we come to the method there, it says repeat 3 to 5 times, but we haven't got time to do that, so we're just going to do one, and we're going to show you how to calculate the speed then. So without further ado, we're going to do the first one at 0.5 centimeters, the depth of water. I know you can't see it because it's blue, but there is actually water in there. Sir, can you show us?
Yeah, so just
lots of water. Okay, let's just check it's 0.5.
So a big sticking point, favourite mistake here. If we notice on the ruler, it doesn't start at 0. Okay, so that's why I ended up needing 2 rulers, because the first thing I'm going to do is I'm going to put it in and I'm going to look at where the ruler...
I nearly dropped my iPad in the
water. Can you see this here? It's getting up to about 0, isn't it?
Bang on 0 there.
I'm then going to get my other ruler and I'm going to measure the distance from 0.
Oh, it's around about 0.5, isn't it?
0.5, yeah.
Good.
So we're on 0.5.
Lovely.
Next thing I need to do then is I need to measure the length of the tray. So I'm getting the distance here. So which side are you showing? This side, sir? And round here?
I would go for the inside.
Inside? Why would you say the inside, sir?
Well, that's where the water is going to... And this tray ain't the best because you can see these little gaps there. But we're just going to take it from, I reckon... Oh, I can't point my finger. There to this side here. And it's going to be difficult with the ruler.
So just going to remember again, then we're going to take 0.5 off. Just because we know that that's there. So I'm going to get this water wet. So I'm up to 30. If I put my finger there then, and I can see the remainder. So I've got about 37, we'll call it, so 37. Obviously, you can see how there's mistakes there with the distance. We could use a tape measure, first of all, to make it a bit more...
Just talking about accuracy, really, aren't we?
Yeah, accuracy there. You could even use, I guess, some laser distance technology.
Maybe.
And you could go to millimetres rather than centimetres to be more precise.
Better resolution.
Yeah.
Loving it, sir. All right, let's do this practice then. So we've got the length of the tray. I should imagine that's going to be the same every time.
Yeah, it's not going to change.
All right, let's do it. I'm excited.
So we're measuring the time for a water wave to go 3 lengths on a tray. I'm just going to get my stop clock ready. Okay, now...
So should we have a trial run? Should we just show?
Should we just show what we're measuring then? So we're going to drop the tray. The only thing you need to be careful of is you don't get
electrocuted
out. I'm going to drop in and I'm going to start timing.
So that'll be 1, 2, 3, and then we'd stop. Okay, let's do it then. I'm excited.
And I'm just going to make sure, if we just show, sir, that we're going to start timing when it hits there. We're not going to start when I drop, because if you think I could start with it drop there, or I could tip it even further.
Yeah.
Okay, so, ready, here we go, sir.
Here we go.
Stop.
1,
2,
stop.
3.
A bit late then.
Doesn't matter though. Doesn't matter. So human error there though, sir, isn't it?
Loads of human error.
We've got the human error. So our time was 4.25 seconds.
Now we've gone to 2 decimal places here, so we need to continue doing it to 2 decimal places.
Okay, yeah.
So we're going to stop the video now. I'm going to come back with 1 centimetre, and then I'll just show you how the results varied. So we did the 1 there. You can see how we got the results, and then we did. We put the tray under the tap, and then we measured out 1 centimetre thickness of water. Well, depth, I should say, not thickness. And these were our results for that one. Okay, reset your clock.
Yeah, reset.
There's 1 centimetre in here now, just to prove it, sir. Come on, just prove that.
You say you don't trust me, is it?
So I know it seems like it says.
So it's going, yeah, and then if I put it in there.
Give it taking that sort of whisker.
Yeah, there you go.
Yeah, 1 centimetre.
So we're just going to do the same thing again now. So I'm going to tip our tray up. We're going to get ready to start. Drop in and go. One, two, three. Bit quicker that time, sir.
I nearly stopped my camera then.
You do?
Nearly did. I was excited. So we're getting quicker now.
Yeah, and we just notice we're keeping with the 2 decimal places.
That's interesting. So already we can see as depth is increasing, the time it takes decreases. I wonder how that's going to affect the speed. Anyway, the next video now you'll see a full set of results and Sir calculating the old speed. And that's exactly what I'm just about to show. So this is the last, so we did sets of results, 1.5 depth, 2.0, 2.5, and then I think we're doing it for 3.0 now. So we've just done the full set of results using 3 centimeters of water. Like I said, there's a lot of anomalous results here because for a start, this was an accurate distance. And we're only taking 1 set of results. We really need at least 3 there. But we're going to calculate speed anyway. And Sir's going to demonstrate how to calculate the speed now using...
S, dt, we got our speed triangle here. So we got S equals speed. Got D equals our distance. And we got T is our time. Okay, now there's 2 ways which we can go about this. I'm going to show.
I just want to stop it there because this triangle that we're using comes from the formula in the front of the book. The exam, which is speed equals distance over time, and that's how it's given. So literally we are just using that formula. So I'm going to continue on with the video in a minute.
You both ways. We've got method 1, method 2. Now, if we notice we've done our time taken for 3 lengths of the tray in each time, but we've only taken the length of 1 tray. So the first way you can work out speed is if I was looking at my triangle, I would cover up S, so I would get D over T, and I'm then going to put my distance in, which is 37, and then I'm going to put my time in, but most importantly, because it was time for 3 lengths, and I want 1 length, I'm going to divide my time by 3. Okay, so I would have for the first one 4.25 divided by 3. Okay. Now the other way we can do this.
This is the easiest way.
This is the easier way. Yeah, we can just times our distance by 3. So rather than having the length of the tray, 1 tray, we're going to now have the length of 3 trays. So I'd have 37, and I'm going to times him by 3, and I'm going to keep my time.
So is that because we saw it go 1, 2, 3, and then we stop the clock?
Yeah.
Right, I see now. So it's like the length of 3 times, and that's how long it took. That's why you're dividing by 3 on the first one, yeah?
Yeah.
Because if you're going to just calculate 37, which is the distance from there to there, you need to, because we waited 3 times, didn't we, to time it? So you would divide that by 3. I think I get that now, sir. And hopefully if I get it, the rest of our year 10 will get it.
Hopefully, yeah. So if we'll just show Sir then that they do give the same answers. And then maybe just quickly, just to show them what we meant. Remember then, our wave goes once, twice, 3 times. Okay, so we're talking about this whole journey. So first time round then, I'm going to use my calculator. And as usual, we're using the woolly way. So I'm going to hit my fraction button.
Ooh,
there.
Like that.
That one there, if we just...
There,
yeah.
oh, lovely.
And then I'm going to put 37. And then underneath, I'm going to have 4.25 divided by 3, and I'm going to hit equals, and I need to hit Scooby-Doo, which is going to give me 26, and just to stick with 2 decimal places, 1, 2, because I'm going to round up.
I see, yeah, you rounded up from...
So we had a 7, so I'm going to round it up.
I like that, sir. It's cracking.
When I'm going to go the other way, personally I think this is the easiest way.
I do as well. It's easier for the calculator
Easier for the calculator. We're just going to do 37 times 3. On the top, we're going to divide in by 4.25. I think it's fine here. Yes. So again,
exactly the same.
Exactly the same. So I would then go and put these values. I've done 0.5. And I'm going to repeat then for the rest.
That's great, that is. So I'm going to take a photo now of the full set of results and then talk about it on the other video, I guess. So there's one more thing I want to add to that video is the fact that we did it 3 times. We waited for the wave to go 3 times to get a more accurate result. If you're just pressing the timer once and then you're waiting for it to go to the end and then you press stop, you know, it's not that accurate then. You don't have a lot of time to think about it. So we do it 3 times and then we'll either divide by 3 if we want to get it per distance, or we'll multiply that distance by 3 to match the time. You can see the full set of results. Where have we got? There we are, the full set of results are there. So, as you can see here, as depth increases, the time taken decreases, therefore the speed increases. So as depth of water increases, the speed increases. Now these results are not very accurate at all. Like I said, we should have done at least 3 or 4 of these, the time taken, and then we should have done a mean, and then we should have done a mean speed. But we didn't have time. And if I just show you what the graph, I mean, this is an example from the 2008 paper. This was the first question on the higher and one of the last questions on the foundation. But you can see it's very similar there. It's got depth of water going down, the wave speed increasing. They've got this relationship, the square root of d here, and that's the sort of how much it increases by every time. So it's proportional to the square root of d. And then if we just have a look at the graph, you're going to get a bit of a curve, just like that. And that's what you'd expect. But who knows what sort of questions they'll throw at you. Maybe on accuracy, maybe they'll ask you why you do it 3 times. Wait for the wave to go 3 times because you're going to get a more accurate result. There's many ways to improve this practical, such as, you know, measuring the distance accurately, better resolution. So instead of using centimeters, we use millimeters. You can see this one that was actually meters there, so that's why it's meters per second. And in ours, you'll see. Let me just put that over there. Ours was centimeters per second. See, so we, you know, because we were dealing in centimeters per second, we didn't have to do anything. But if it wanted in meters per second, we would have had to do a bit with that. We would maybe had to gone down to millimeters first and then times by 1,000 then. But if you know there's 100 centimeters in a meter, then you would divide these by 100 then, because be smart, mate. So be smart, mate. Stop being dumb. If you're going from big to small, you're going to multiply by it. In this case, we would have been going from small to big up to a meter. Therefore, we divide by it. So hopefully that's some help there.